Okay, now let's enter the topic of linear regression problem. So we can think of this linear regression model as a supervised learning problem. Okay, so for example, using if we want to predict the housing price, okay, of San Diego, and the label we want to predict is a continuous number here, a continuous number, which we call a label. So we can denote it by y variable, okay, or in some statistic books or other disciplines, it's also called dependent variable, okay. And the feature we want to use is a bunch of other features, okay. A bunch of numbers collected about the house itself, like the size of the house, the number of bedrooms, school district, year, okay. And it's a very typical supervised learning problem, okay. So one thing that we want to pay attention here is that the label here is a continuous number. It is not a binary classification. For example, in the salmon versus sea bass problem. Okay, so that's why it's called a regression problem. Okay, so if it's a discrete label, say the label has only 1 or 0, 1 versus 0, then it's called a classification problem. But in this case, it's called a regression problem. Okay, so now let's start from the simplest case. So we just consider one feature, okay, or a single feature. Then in this case, it's called simple linear regression model. Okay, for example, we just use the size of the house as the only feature or only predictor to predict the price. Okay, and we plot the relationship or the scatter plot here. For example, for the house of 500 square feet, the price is somewhere below 200K, right? If it's 1,000, then it's almost 200K. 1,500 square feet above, okay? So say that's the only data set we've got, okay? So what can we tell from this plot? We can basically see a general increasing trend, right? But here we want to model those data or use some linear models to describe the data so that we can use the model to make predictions, okay? And we put the training data here. For example, the training data is in such a format. The first column, that's the feature. The second column, it's the label, right? Feature label, we call the feature X and label Y. So here we use some notations, okay? So, and these notations will be, they're actually a convention of the field, and we will keep using them in future lectures. So here, the number within round parentheses, round brackets upon the corner as superscripts, and these numbers indicates the instance number. So the 1 here indicates that this is the feature of the first data point, and the 1 here indicates this is the label of the first data points. Okay? And the 2 here indicates this is belong to the second data point, and this second data point, and the 3 here. Okay, so this number indicates basically how many data points you've got. Okay, and because we have only one feature, so we simply need to use one parameter. Okay, so this is the first time we introduced the notation for parameters. Okay, and we use the Greek letter theta. Okay, and this theta 1, notice that here the 1 is at the lower corner. It is subscript. So this subscript 1 indicates that this is the first parameter. And actually, in this case, there's only one parameter. Okay. And the idea is that we use the product. We use the product between the parameter and the data and the feature to make predictions. Okay, so this is the simple idea that the linear regression model holds. Okay. So now let's go back to the mind map of machine learning models in general. So we replaced the text in the middle to these parts, okay, through you can think it of a vector, a column vector, okay. We replace the parameter settings to be this way, to be a parameter vector. So the parameter vector has two elements. The first one is theta subscript 0, and this is theta subscript 1, okay. So we have additional parameter, which is, clean up this a bit. So the additional parameter is theta 0, right? Because in the previous slide, we said that only one parameter is enough because we just have one feature, which is the size. But why do we need this big theta of 0, theta subscript 0? Because this theta 0 models the intercept, okay? We'll see that if we don't have the theta 0 parameter, if we just have theta 1, then the model will cross the 0 points. And we don't always want that. We want the model to be flexible so that it can have positive intercepts. All right, so the goal is to learn a linear model, okay, that maps the feature to a label y, okay, and we write the linear combinations into a function, okay, because this function f uses theta as its parameters, so we use f superscript theta as the form of the function, okay, and the mathematical expression is theta 0 plus theta 1 times x, and this is a very typical linear combinations, which we will the term we will use a lot frequently in the future. So it is a linear function of x of the feature. Okay, if we plot y against x of such a function, okay, so now we don't know the values of theta 0 or theta 1 yet, but if we plot any function like this, it will be a line like this. Okay, and the theta 0 and theta 1 are the model's parameters. Okay, so the theta 0 is somewhere here, right? When x is 0, this is the value of theta 0. And theta 0 gives us the flexibility to move this curve upwards or downwards. All right, so given a trained model, we want to make predictions. The way we want to make prediction is also straightforward, right? So a trained model, so here notice that, assume that we already trained a model, and that means we know the thetas already, okay? So the trained model means that we already have numbers to theta 0 and theta 1, okay? And using these parameters, we can simply make a prediction of a house that is 895 square feet by times theta 1 with this number, make the product, and plus theta 0. So the simple computation gives us the prediction is 268,000, more than $268,000. Okay. So now we can further look at the meanings of the parameters. Okay, theta 0 and theta 1. Now, what if our theta 1 is 0? That means our slope is 0. The y doesn't change at all when x changes, okay? And what if the theta 0 is 0? And that means the line will cross the 0 points. And when x reaches 0, the y also reaches 0. Okay? And in most cases, none of theta 0 or theta 1 are 0. So this is a very, the blue curve is, the blue line is a more typical case of a linear model. Okay, so the next problem is that with this setup, okay, with one feature x and with two parameters theta 0 and theta 1, how do we find the best thetas that fit the data?